A warm welcome to you for our second event celebrating the centenary of the Department of Materials Science and Metallurgy. The history of our department can be traced back to the generous donation of the Worshipful Company of Goldsmiths that resulted in the opening of a laboratory dedicated to the study of metallurgy on the 5th of October 1920. My name's Ruth Cameron, and as joint head of department, it's a real pleasure to be able to welcome you all here today to participate in another event exploring the impact of our department and its researchers. Today's speakers are Professor Sir Harry Bhadeshia, Tata Steel Professor of Metallurgy. We've got Professor Zoe Barber, and we've got Joe Smith. Professor Bhadeshia is a world-renowned expert on the physical metallurgy of steels. Professor Barber is a world expert in thin film deposition and a member of our device materials group, and both have been extensively involved in university teaching. Joe Smith from Magdalen College is a master's student in the department, and last year was a winner of the Worshipful Company of Armourers and Brasiers Departmental Prize.
Thank you, Ruth. So we are this year celebrating the department's 100th anniversary from its initial creation within the Department of Chemistry. And the story really begins with Charles Haycock, who was elected to a fellowship of the Royal Society in 1895. And that was just 15 years after he took the Natural Sciences Tripos at Cambridge. His work, which was based in the small laboratory in Sydney Sussex College, attracted the attention of the Goldsmiths Company, which endowed a readership in metallurgy at Cambridge and the Goldsmiths Laboratory of Metallurgy. Harry, did Haycock, who initiated metallurgy in Cambridge, write any books?
No, in fact, he didn't. But he did inspire Ulrich Evans, who was studying for the Natural Sciences Tripos in 1909, and was fortunate to be supervised by Haycock, who enthused him about metals and alloys. And this led to his interest in electrochemistry of metals, but his work was interrupted by the First World War. When he returned to civilian life, he began his famous studies on corrosion, which were to last for 60 years. He often referred to corrosion as the unmaking of metals. Now, he was given access to the Goldsmiths laboratory by Haycock, and he was welcomed into the Laboratory of Physical Chemistry by Professor Lowry. And when the Goldsmiths chair and Department of Metallurgy were subsequently established, each holder of that chair counted it as a great privilege to provide Evans with facilities. So this is how science worked in the old days. You know, the head of department actually provided all the facilities.
Yes, and it explains why the head of department is always acknowledged for the provision of laboratory facilities in older papers from the department.
That's right. So the first book ever to emerge from the Department of Metallurgy was by Evans. And this is just volume 1 of a 4-volume set that he published in 1923. And even now, it's quite fascinating to read because, you know, it contains, for example, information about the colloidal state of metals and the precipitation of one colloid from another. And bearing in mind that this was written just 10 years after the Bragg law was discovered, it really is an amazing piece of work. And the other 3 volumes systematically go through the periodic table as far as metals are concerned in the sequence that existed in those days. Now, when he wrote these books, he realized that the subject of corrosion and oxidation was very badly understood in those days. You know, people used to think that corrosion is similar to putting a piece of metal into acid and it would dissolve. And Evans was the first person, well, one of 2 people in the world who believed that corrosion had an electrochemical basis. The other one was Wustenberg. So, you know, we do experiments in schools where we put a droplet of water on a piece of steel, and the droplet is laced with phenolphthalein and ferricyanide. So you get red and blue colors for the anodic and cathodic regions. And that is the key feature that Evans actually published in his next book, which was in 1924, the corrosion of metals and established the electrochemical basis for corrosion, originally and first published in this book. Now, Evans obviously was a great scientist. You know, he contributed for 60 years, actually. But he also had a life outside of his science. He was very fit, and he swam in the River Cam, for example, and enjoyed climbing. And legend has it that he narrowly missed taking part in an expedition to the Himalayas. And his final book was published in 1964 with the amazing, wonderful title, Outdoor Activities, Memories Selected for Amusement Rather Than Achievement. And, you know, you can find this book in King's College Library if anybody wants to have a look at it.
Mm. And wasn't John Chilton, who became a lecturer in our department, one of his PhD students?
Yes, indeed, he was. And he wrote The Principles of Metallic Corrosion, which was published by the Royal Institute of Chemistry in a series of monographs designed for teachers. So John's book was number 4 in that series. And he was a wonderful teacher. You know, I've experienced him myself. And his Charles Beatty lecture at the Royal Society of Arts, which is available on the internet, is an exemplar of science communication for a broad audience at a time, you know, when there were no courses on how to communicate your work to a general public. So he was a brilliant teacher.
Dr. Evans was obviously a great scientist who enjoyed science and life at the same time. Some of the books I've come across are by Alan Cottrell. His yield point effect, described in the Theoretical Structural Metallurgy, still forms the basis of teaching when it comes to the stress-strain curve. What's the story there?
Okay, so that particular book happened during the winter, just after the Second World War, when Cottrell had to work from home, rather like we are doing right now, because there was a national fuel shortage, which meant that you couldn't do any experiments or have heating at the University of Birmingham, where he was then based. So this isolation led to the famous theory of the yield point effect, due to the anchoring of dislocations and culminating in the classic book published in 1948. When later he joined Cambridge as the Goldsmiths professor, he was asked to publish a second edition, but he decided instead that there was a good case for writing an elementary but specialized book on a book which illustrates the triumph of metallurgy. So in 1966, he published Introduction to Metallurgy. So this is a book that I bought as an undergraduate, and it's actually a signed copy. So I got Alan Cottrell to sign it when I joined the department back in a long time ago. Okay, so this book actually is published by the same publisher, Edward Arnold, as Ulrich Evans' first book. And a part of the content reflects Alan Cottrell's lectures on extraction metallurgy to the Part 1B class. And the late Brian Ralph once told me that the secret aim was to cover the entire syllabus of the 1B metallurgy course, which he manages to do actually. So this might be the first book ever written to cover an entire course. In his own words, it's a complete survey of the metallurgical field. And it's interesting that later on, when I was the books editor for the Institute of Materials, along with Mark Hull and Peter Dankworth, we asked Cottrell to do a second edition, which means that the book still is available in print.
Yeah, the cover of the second edition was from George Smith, I believe, and his co-workers at Oxford, a direct image of those Cottrell atmospheres of carbon atoms around the dislocation line in steel. Not surprising, but nevertheless remarkable to actually see the carbon confined to the strain field of the dislocation.
So you're quite right. You know, Cottrell did not think that the response of matter to stimuli could be understood without atomistic principles. So in 1964, he published this book, which is The Mechanical Properties of Matter. If you look closely, there's an image there in which each dot represents an atom. And this particular image was taken in our department showing the atomic structure of tungsten, and was taken by Ranganathan. And it was Cottrell who actually initiated the feline microscopy group in the department, because as he explains in the preface, you really need to understand structure at an atomic level to explain many of the properties that we see, not just mechanical, but physical properties as well.
And of course, Chris Pickard is now the Cottrell Professor, and he also works on atomistic methods. Given that engineers deal with much greater scales, did Cottrell have any reservations about these methods?
Yeah, so let me just comment on Chris first, because he, along with Mike Payne, developed CASTEP, which is a computer code that is now standard for atomistic calculations. So for example, if I wanted to explore a hypothetical structure such as iron in the diamond arrangement of atoms, I could do that with that software and work out whether it's even slightly likely that I could create it on Earth. So it's a very powerful piece of software which is used all over the world. Coming back to Cottrell's reservations, I recall a meeting in London which he organized with Pettifor from Oxford on atomistic calculations, where he explained that powerful as these methods are, they do not provide insight or deal adequately with deviations from stoichiometry, because you're limited to a certain number of atoms to cope with the computational load. So he began to write books on this subject, and one of those books is the chemical bonding in transition metal carbides, and he gave me a copy of this, and this too is inscribed by him. And in this book there is an equation showing the repulsion between carbon atoms. So the idea of this book is that he wanted to do calculations without using a computer. So he managed to collect data on bond strengths and so forth, and work out cohesive energies and the stabilities of the transition metal carbides. And the particular equation I'm referring to, I took that and I applied it for carbon atoms inside iron, and it worked pretty well and was consistent with thermodynamic calculations. So a certain amount of semi-empiricism actually helps you to get intuition into why certain carbides are more stable than others, rather than just looking at cohesive energies. And he went further. He published the book on concepts in electron theory. This was the last book that he published. And in fact, Jeff Cottrell, his son, who is a plasma physicist and an amateur astronomer, set up Alan Cottrell's computer so that he could dictate this book into the computer at the time. So in this book, he tries to explain electron theory, the theory that goes behind the computations, in a very simple and elegant way. And in fact, he gave a course in our department using this book. So, sorry.
Are there any other books other than Cottrell's Introduction to Metallurgy that cover an entire course?
Yes. So with EPSRC support, Harry and I developed a one-year master's course on materials modelling, and this led to the textbook Introduction to Materials Modelling, which I've got here. That was published in 2005. And it was unique, really, in that it covered the whole range of modelling scales, from atomic to engineering scale. And it's remained a routine part of the undergraduate curriculum, where the book continues to be very much used. And I think it's worth noting that the content of this book remains extremely relevant. It's a kind of fundamental text which really hasn't gone out of date.
Yeah, and there are other books that Cottrell wrote. Perhaps the most notable one is, how safe is nuclear energy? Because there was a period where there was quite a lot of uninformed discussion, and phrases like the malignant growth of nuclear power stations, and how safe is radiation and so on. And Cottrell deals with all of that in this book in a very readable manner. And he actually had a seminal role in ensuring the safe operation of nuclear plant for energy generation. So this is a valuable contribution to, if you like, set the record right in an honest way, which presents the pros and cons of the whole subject.
Alan Cottrell was followed by Robert Honeycomb as the Goldsmiths Professor in 1966. And he was head of department for more than 18 years. He was head of department when I arrived. During that time, Honeycomb published 2 books, The Plastic Deformation of Metals and Steels.
Both of these books cover structural property relationships, which seem really to be the essence of materials science. And the Steels book forms the basis of part 3 course with the same title. What's the story behind this book?
Yeah, so there's a really interesting story, actually. The Steels book was supposed to be written by David Edmonds and Professor Honeycomb, but David was on a Royal Society research fellowship, and someone at the Royal Society suggested that he should be focusing on research, so he had to drop out. Honeycomb completed the book, and he asked various members of his research group, which was known as the Steel Group, to comment on specific chapters. And I was asked to look at the chapters on martensite and bainite. But at the time, we disagreed on the mechanism, the choreography of atoms during the bainite transformation. So I commented only on the chapter on martensite. And bear in mind, that I just completed my PhD in his group, and yet he respected my views, a perfect example, if ever one was needed, of the quality of academic freedom in Cambridge, and I'm sure in other places as well. Now, I do remember a pleasant discussion where he joked that, if I went down alleyways, then I was likely to get mugged.
So how did you come to be the co-author of the 2nd edition of Steels?
Well, by that time, I had published my own book, Bainite and Steels, and I gave him a copy. I gave Honeycomb a copy. He studied it, and he was apparently convinced, and told me that I had a free rein to change the chapter on bainite and to add 3 more chapters and do a general revision of the whole book. The book is now in its 4th edition with translations in Korean, Malay, and the traditional Chinese languages. So, for example, this is the Malay version, where keluli means steel in the Malay language.
What prompted you to write the bainite book as opposed to continuing to publish papers on the subject?
So when I started research, the subject was in utter confusion, with heated, largely unconstructive and quite lazy debates in the literature. So I felt there was a need to present a coherent picture that is consistent with all of the available evidence. The 3rd edition has this year been translated into the Chinese language by my wonderful colleagues at Yanshan University, Zainan Yang and Fucheng Zhang. Now, Zainan was a visiting scientist in my group, illustrating nicely how events, conspire to lead to scholarship, because the amount of work involved in translating, something like a 650-page book is just enormous. Even the figure captions have been translated. Now, let me add that in the same series as the Steels book, Ian Hutchins in our department, he wrote a really nice book on tribology, covering the friction and wear of engineering materials. And this is my cherished signed copy that I refer to today in my research on the wear of steels, and in particular impact wear of abrasion-resistant steels.
Turning now to John Knott, who was in 1966 and apparently out of the blue invited by Professor Honeycomb to come to Cambridge from the Central Electricity Research Laboratories. His book, Worked Examples in Fracture Mechanics, is an excellent illustration of a text intended for teaching, but which is also a perfect resource for researchers. But before that, he published Fundamentals of Fracture Mechanics, which begins with a quote from Boris Pasternak's Dr. Zhivago, in which Antipov complains about the failure of rails in cold weather.
That's right. Well, John was a special person. He had a deep knowledge of many aspects of metallurgy. And in particular, he understood more than most that the study of microscopic mechanisms must be accompanied by quantitative methods that allow engineers to design safe structures. So this attitude actually served society very well when for many years he was on the independent technical advisory group on structural integrity, commonly known as TEGSI, in the context of nuclear safety. And he was there at the foundation of TEGSI, and he served as its chairman for 7 years. So he did an enormous amount of very detailed work to check that the structural integrity of nuclear pressure vessels and other components are safely calculated. Now, this book on fracture mechanics is necessarily heavy on mathematics, but it's written in a manner where the concepts are clear even on a first reading. So he made an effort to suggest different pathways to the book so that you could skip some of the difficult parts and focus on the essence of the subject. And I think that is quite important so that the book does not pose an insurmountable challenge to many of the readers. And those who want to go into detail can, of course, do so.
Didn't you write a book in the Worked Examples series for the Institute of Metals?
Oops, sorry, my pile of books just fell down. Okay, can you ask again?
Yes, I was just saying, didn't you also write a Worked Examples book for the Institute of Metals?
Yes, that's right. So that was in 1987, Worked Examples in the Geometry of Crystals. But this was for a graduate course that I gave in the department, and it deals more with the mathematical handling of orientations, deformations, interfaces, and phase transformations, solid state phase transformations. It basically assumes that you have a working knowledge of crystals, and both John Knott and Jack Christian in Oxford commented on this to help me to improve the draft, and duly acknowledged. But the interesting thing is that when I taught the course, it helped to clarify many aspects which I took for granted during research, but which I found I did not fully understand until I was challenged by students. So that's one of the advantages of giving a course and writing a book on the subject.
That particular course now no longer exists, but you continue to teach crystallography now to undergraduates.
That's right. So recently, I published a much expanded version to cover the latest developments in the mathematical methods, and included 9 additional chapters to cover also the elements of crystallography. So undergraduates can basically ignore what comes after 9 chapters if they wish to, or they can be inspired by them. That's the logic of this particular book. And I've taught crystallography to the Part 2 class for a number of years. And if you look in here, you remember many of the things that we discussed at the time.
There are so many materials already available today and claims about how the latest discovery is going to change the world as we know it. How are undergraduates expected to make reasoned arguments and appropriate choices for better design? What's the university done to address this difficulty?
I think that's a very important question, especially in today's world. And there are 2 things that have happened in the university which stand out. So Jim Charles, who was a wonderful teacher in our department, but was also well versed with industry. You know, he started his career in the British Oxygen Company. He wrote the book Selection and Use of Engineering Materials, which is now in its third edition. And the book correctly emphasizes the need to consider a bank of properties. And, you know, to paraphrase colleague Dan Miracle, there is much work between measuring a single attractive property to demonstrating its credibility in a particular application. You know, very often claims are made about the wonder of a material by just focusing on a single property, which doesn't actually help to design a component. So along with Jim's book, we now have the Granta software created by Mike Ashby and his team. And Mike Ashby was actually an undergraduate in our department, and he did his PhD in our department under Jerry Smith, the late Jerry Smith. So if you combine Jim's book and the software, then we have a winning combination. Now, I'd like to add that, you know, Mike Ashby is a renowned author in his own right. He's written many, many books, but unfortunately, he wrote them while he was in the engineering department, so we're not going to cover them today. There is another book that Jim Charles wrote, and this time with Lindsay Griffith, and it's called Light Blue Materials. It's a very interesting book. It covers the history of the department all the way from 1920 to 2005 when it was published. And Jim Charles also published a biography and an autobiography. Jim, his book was called Out of the Fiery Furnace, Recollections and Meditations of a Metallurgist. Now, it's a very personal book, but it makes interesting reading because, you know, it contains a mixture of metallurgy and his particular way of dealing with it. He continued to write books, and there's a further one known as One Man's Cambridge, which is even more personal, covering his father's life and achievements.
So you mentioned Lindsay Greer there. Lindsay, of course, also features through the book with Ken Kelton on nucleation in the condensed state.
Yeah, so this is a book. This is the book, and it's about 730 pages. It's really the most comprehensive treatment on the subject, and you know, it doesn't neglect the complexities that arise during nucleation. For example, you know, when the treatment of very small clusters of atoms and the meaning of an interface on that scale, all that is covered. And the book is dedicated to David Turnbull, with whom Kahn and Lindsay worked at Harvard when Lindsay was on a NATO fellowship at Harvard University, and also dedicated to Robert Kahn from our department, who inspired them to write this book in his capacity as the inaugural editor of a new series for Pergamon. I'm certain that the book represents the standard in the subject, and it took 19 years to write, okay, 19 years. And a number of Lindsay's colleagues lost money because they bet that the book would never be completed.
So that brings us nicely to Robert Kahn, who was responsible for the publication of many, many edited books after he was welcomed back to the department in which he'd been an undergraduate. Yeah,
so of course, he is very famous for vast volumes of edited books, but he also wrote 2 by himself. So this is Artifice and Artifacts, which contains 100 essays on material science. It's an adaptation of articles that he wrote for Nature and other journals, covering a vast range of subjects. For example, how to detect fraud in the labeling of wine. You know, he was quite a character. The second one, The Art of Belonging, memoir, is more personal, almost a biography describing this grand old man of science, our own grand old man of science. And as I pointed out for Ulrich Evans, there are actually a number of books like this that illustrate the person behind the exceptional science. So Colin Humphreys, for example, at a ripe old age, published a paper on three-dimensional graphene and has gone on to create a company which has probably marketed the first ever viable electronic device made from graphene, the thinnest and smallest Hall effect sensor, which is due to be installed during the refurbishment of kilometers of the CERN synchrotron. Now, at the same time, he found time to write two books on the interpretation of events in the Bible, the miracles of Exodus and the mystery of the Last Supper.
Mm-hmm. So moving topic now to liquid crystalline polymers. Harry, in the early days, this appeared to be a strange contradiction of spatial order, fluidity, and large molecular weight. But nevertheless, we have the solidified form Kevlar, which is now almost a household name. Tell us about the book by Athene Donald and Alan Windle.
Yeah, so Athene was actually in our department as a Science and Engineering Research Council. Today we call it APSERC. So she was an SCRC fellow for 3 years before joining the Cavendish laboratory. And Alan Windle, of course, had been in the department for some time covering the general area of polymers. Now, when they worked together on specific aspects of liquid crystal polymers, they were surprised to find that there was no dedicated text on the subject. So they wrote Liquid Crystalline Polymers, which was published in 1992 as a complete story, all the way from history to the sort of detail which would inspire the reader. And there was a later second edition published with Simon Hanna, who was also from our department and now is a professor in Bristol University.
So could Athene be the first female book author from the department?
I think that is right. You know, although she was based at the Cavendish when the book was published, liquid crystal polymers work originated from our department. And of course, she went on to achieve much more in soft metaphysics with Sam Edwards at the Cavendish. And you might be interested that she writes a well-researched blog on a variety of topics, occasionally delving into the trials and tribulations of being a scientist.
And now to crystallography. The department has a reputation for rigor in its teaching of this subject, and almost half a century of teaching collaboration with the Earth Sciences department. I suppose it's not surprising that there have been a number of crystallography books published.
Indeed, we now have the book by Kevin Knowles and Tony Kelly, now in its 3rd edition.
And I have the 2nd edition here. This is my copy. So
excellent. The 1st edition was by Kelly and Groves, and when Tony Kelly came back to our department, he and Kevin connected because they both have a reputation for meticulous attention to detail. And there is another connection that Kevin was actually supervised for his DPhil in Oxford by David Smith, who in turn had done his PhD work with Kelly. So there is another clear connection here.
And the book on metal matrix composites by Bill Klein and Phil Withers has the title Introduction to Metal Matrix Composites, but is in fact a comprehensive treatment of value to both undergraduates and researchers. Are there others that Bill has published?
Yes, the book Introduction to Composite Materials with Derek Hull, who was the Goldsmiths professor after Honeycomb. So this has become one of the standard books in the teaching of composites. And the latest edition explains, for example, why graphene polymer composites are ineffective. Now, let me ask you a question, Joe, just to get your view on books. So can you, as a current undergraduate, give an opinion on the utility of writing books in this day of the internet and electronic access, online access to all sorts of knowledge, is it a worthwhile thing to do given the enormous effort involved in writing books?
I definitely still think it is. From what I've seen, books both help to define a subject where there's often a large mass of disorganized knowledge, and also present a coherent, often big picture assessment whether that's for teaching or research. But certainly it seems that books today have been made much more accessible by the internet, and this can only be a good thing.
And I think the effort involved in writing a book is worthwhile, even if it clarifies the subject for the author alone. But also by discovering inconsistencies, the process can even generate research.
And the fact that some more recent books are backed by snippets of online software, particularly that included in Do-It-Poms, is incredibly helpful in really deciding whether we understand what we read and in making topics interactive for learners.
Yeah, I think there are also other benefits. This book, for example, is hot off the press, Innovations in Everyday Engineering Materials, written with Tarashankar Debroy at Penn State University. And here's another one, which was rushed over by the publishers for this event, Theory of Transformations in Steels. Now, when the first hard copy arrives, okay, there is a stunning sensation of joy. And you know, the word stunning actually, word stun actually means to incapacitate. So you're not able to actually do anything useful for the next few days after staring at the hard copy of the book. And for a microsecond, you feel that you're in the company of J.K. Rowling's or Chinua Achebe. And you have to remember, you know, a microsecond is a long period of time. It is 1,000 times as long as a nanosecond. So thank you all for listening, and it's now time for questions and answers.
Okay, I don't seem to be able to turn my video on for a minute. I think the people in charge of the Zoom call can perhaps bring that on for me in a second. But can you hear me? Oh, here we go.
Yes.
I think I can now start my video. Fantastic.
Yeah.
So thank you very, very much to all three of you. That was an absolutely fascinating whiz through 100 years of books, a whole century of work going on there. We've got some questions already, but I would encourage everybody in the audience to type your questions into the chat. We've got some time to get our panel's views on these questions. So let's start with a question for Harry to begin with. And this is from Ananth, who says, it's a very impressive journey towards book writing, but how did you get into the discipline of putting together all your thoughts into a book? They say they've been trying to put together their thoughts for a long time into a book, but it doesn't seem to be moving forward. What's your advice?
I think the first book basically came from teaching, and in teaching, you know, you have to actually learn things which are not in your area of expertise. So you're forced to actually learn things and put them down in a logical order for the students to appreciate. So that's how the first book that I wrote came about. And the second book really came about from intense irritation at the state of the subject. So there is a strong motivation to do something useful and to present a coherent picture. But you are, of course, doing many other things at the same time. So for example, Lindsay Griffith's book took 19 years to write, and he went through being head of department for 7 years and his research group and all the rest of it. So it is something that's worthwhile, but it's not for the faint-hearted.
Fantastic, thank you. So Admir Shiradzi is saying, is it true that that Cotterill predicted the existence of dislocations well before TEM proved the existence of his theories? And his second question is, how do you see the future of metallurgy and materials in the department, as it seems that fewer people are researching metallurgy these days in materials departments?
So is that addressed to me?
Let's start with the Cotterill prediction of the existence of dislocation. So Is that something that you want to comment on?
Yeah, so it wasn't actually Cottrell who predicted the existence of dislocations, but you go back to Taylor and all those people in the physics department, Cavendish and so forth. And even going back to the 18th century, Volterra had the operations which described the displacements due to various kinds of cylinders being cut and then joined together. Yeah, so Cottrell's theory of structural metallurgy was actually a beautiful compilation of dislocation theory. And of course, he contributed to things like Lomo-Cottrell locks and the strain fields around dislocations. Elizabeth Yoffe, who was in our department actually, she was the first to calculate the strain fields around dislocations, using elasticity theory. What was the second question?
It was about the future of metallurgy as opposed to more general material science. Have you got any comments on that?
So it's never a good idea to predict the future or to try and change the past. That's my opinion.
Very, very wise, very wise. So I think this next question is probably for everybody. So maybe starting with Zoe. So which of the books discussed would you take to your desert island?
Oh, I think probably a crystallography book, because it's meaty stuff there, and I've always, I mean, it's why I'm still around. I started natural sciences thinking I was going to be a physicist, and I, like many people, discovered materials through the first year crystallography courses, which just appealed from the sort of solving clues, crossword solving point of view. I always say I find it very, very satisfying, and there's just so much there. You can keep delving into crystallography and find more and more, I think.
Yes, I agree. Thank you. Joe?
Oh, I hate to copy Zoe, but I was thinking certainly the book I've used most recently is one that I currently have in my room back at college, which is Harry's worked examples on the geometry of crystals. And similarly to Zoe, I just find that crystallography is an incredibly satisfying subject to look at, because it reduces down a lot of these problems to wonderful ideal problems that you can look at from a very logical point of view.
So in the preface of this book, I actually put down the book that I would like to take if I were to be abandoned on a deserted island. And the book is actually this one. You can see how used it is, okay, and bedraggled. And it's The Theory of Transformations in Metals and Alloys by Jack Christian from Oxford, which is an absolutely amazing book. It is so beautifully written, concise, and yet you have to read it several times to understand it because of its conciseness. So I spent a whole sabbatical actually reading this book a long time ago.
Thank you. So some recommendations there for people for bedtime reading to get into the subject. A question for Harry from Hongbao Dong. If the research field is not established yet, when would be a good time to write a book to introduce the field while the field is still developing?
So most people would argue that the best, initially there should be reviews, because if the subject is changing rapidly, then you're likely to have your book out of date very quickly. So I would suggest that, writing reviews is a good thing. And these days you can publish very large reviews in journals like Progress in Material Science, 100 pages, 200 pages, etc.
Okay, I think a question perhaps for Zoe next. I'm just finding my list of questions here again. Do you think universities encourage academics enough to write books, or are universities not really giving academics space to do that?
Well, clearly I don't have experience of other universities. I guess there's encouragement from the point of view of output. We're always encouraged to have quantifiable outputs. I fear that there isn't enough time. And as I think Harry has said, it really does take a lot of focused effort, and it's very, very difficult. I've been approached with, you know, ideas from publishers, write a book on thin film deposition, thin film growth, and I'd love to do it, but it's a huge body of work to do properly and to do well. So I think the answer is probably that there's discouragement from the point of view of just not having enough hours in the day. Some brilliant people can do it, Harry can do it, but many of us just haven't got the sort of energy to do so.
So I guess related to that, Colin Humphreys is saying, he said, great interview. He says, what's your technique for writing books, Harry? What do you write every day? Do you write at a set time? How do you make yourself do it?
So in my later years, I actually learned from Colin Humphreys that the best time to write is early in the morning. You know, you get up at around 6 o'clock in the morning and spend a couple of hours doing the work. But it cannot be every day because many other things get in the way. So if the subject interests you sufficiently, then you'll make progress over a period of a couple of years or so. But the early morning period, I find, is very productive.
Some hints for us all there. So this one's possibly for Joe. John Spear says, in the USA, there seems to be a trend where university textbooks are quite costly and the students are trying to avoid purchasing them, which then drives the community to find free alternatives to books. Is this also happening in the UK? And are there any clear implications for education and book publishing? It's a broad question. What are your thoughts?
I think certainly from what I've seen, the books in the UK are nowhere near as expensive as those in the US. But also I haven't had to purchase any books for my studies, even where they've been recommended. So mostly I rely on sort of a college library or departmental libraries that have all the textbooks I'd ever need and sufficient copies of them. And alongside that, the Cambridge courses are usually fairly self-contained, and so the books are actually quite difficult to fit into your schedule to read around all the other work you have, and are usually kept for the vacations if you sort of want to have a read of it.
So kind of related to that, it's perhaps for everybody, but do your students use the textbooks in paper format or digital? So the person asking the question is saying, personally, they prefer a paper-based book rather than having it on a screen. But so Joe, do you have a preference for seeing it on a screen or holding it in your hand?
It's certainly very paradoxical because everything points towards electronic books being better. I can carry thousands on one device, and they are much more compact. And often cheaper as well. However, there really is some lovely feeling about having a paper book that will always drive me to get the paper book if I can. But certainly in the last year, the availability of electronic books has been fantastic while we haven't had access to libraries.
That's very true. Harry, do you like having it in your hand or?
Yeah, so I think it depends. You know, if you need to study something in great detail, then the electronic version doesn't work. The electronic version often is where you want to get snippets of information. But if you want to go through the whole book systematically, then I think there's nothing to beat a paper copy.
I think also you can have them on your bookshelves and come back to it and remember it. Whereas if it's filed away on the computer, you'll maybe forget it's there. It's lovely, the idea that you just sort of pass a book and think, oh yes, I remember that, and can look something up or something like that.
So perhaps for Joe, this one, what books should be written to attract sixth formers into material science in the first place, without them needing to actually accidentally stumble into it, for example, on the natural sciences tripos? What should be out there? What should somebody write?
That's a very good question. And actually, I might not even be the best person to ask nowadays because I've already discovered material science. But certainly when I was applying to university, there was a sort of more popular science book that I read called Stuff Matters. that I know is very popular among people sort of preparing for a Cambridge interview to get an idea of what material science is like. I still don't feel it completely gives you a sense, because I certainly didn't realise what materials was entirely like until I just did the first year course. And that's possibly because any book that is tries to be amenable to a general reader necessarily doesn't cover topics such as crystallography in the kinds of depths that I think makes them really interesting. So I don't know, I think that is an open question, but I'd certainly be interested to see any possible solutions to it.
We have our recommended books for the Tripos with the Stuff Matters, Mark Miodovnik, and also Gordon Structures, which was the classic for my generation to pull us into materials, I think. I'm nervous about crystallography textbooks, perhaps putting people off, but despite what I said earlier.
So Zoe, this is a teaching question really, and it's what distinguishes a good book for undergraduates from a comprehensive book? What makes something really good as a teaching text?
Oh, that's a tricky one. I guess I'm trying to think what's the other side, what's not the teaching text? Is that a text that's trying to attract readers without perhaps crossing the T's and dotting the I's, which is frustrating if it's an undergraduate text. I think an undergraduate text has to be complete and sort of justified. You can't get away with breezy statements about things. But I can't think of anything else there. I don't know. I wonder, Harry, have you got a comment on that one?
Well, I think the Open University does a really good job there. You know, so you have these books which are not very thick, but are so carefully put together that they explain the topic with incredible clarity, and yet they provide a level of challenge, because you don't want a book which is just perfectly understandable. Otherwise, you know, it's like sport, you need a bit of competition. So I think a book like that would require a great deal of work, you know, with people looking at how it's going to work and focus groups and so on, which is what the Open University does extremely well. The other problem, I think, in having a course book is we often change the course when we give it again. You know, the course content is always changing. So in that respect, a book would not be helpful.
Yeah, thank you. So we're probably coming towards the end now. There are a lot of questions here that we haven't been able to come to. But we're being asked, is there a list of books published? Harry, would you like to comment?
Yeah, from the department, you mean? Yeah.
I guess, yes.
Yes, so I've got all that ready, and our aim is to link that list to the video of this presentation today, which will be available on the department's and the university's YouTube channels.
I think we're also trying to pull together a list not just of the books that have been authored from the department, but those that have been edited from the department as well. And I think Kevin Knowles is doing some sterling work in that area too. So we're pulling together that information, but the information from this talk you'll be putting on the website.
Yes.
Fantastic. Well, I think we'll draw it to a close there. So firstly, I should say thank you very much to Harry, Joe and Zoe for that really thoughtful presentation, and to everybody here for joining. We've had a huge number of people here on the call, and that's it's been fantastic. Just shows the interest that we've got. I've learned a huge amount from today's discussion. Again, I've been really struck by the contributions of our department over the years to leading the way and defining the field of material science. I think as researchers today, we often find ourselves focused on journal papers alone as a research output, but today has been a fascinating demonstration of how the discipline of writing a book can be a way of drawing together ideas And please continue to follow the department for announcements regarding future events for our centenary. So once again, a final thank you to our speakers and to you for attending, and we'll close there. Thank you.